which is pretty much important when we are designing a process or any product. So any physics-based simulation or any simulation which can help in reduction of physical resources is pretty useful for product development or for any assessment of the process. Then we have system integration, how different things are integrated. For example, the navigation of the robot and then kinematics of the robot to handle items at a specified location. So, and then transferring that data to the inventory management system. So the system integration is very important aspect of Industry 4.0. Likewise, we have several aspects like Internet of Things. Then we have cyber security. So if everything is kept in the digital form, then cyber security becomes very important. Then cloud computing is one such part or aspect of Industry 4.0. And then definitely additive manufacturing, which is nothing but a digital way of manufacturing components. So that is also the framework of Industry 4.0. Then augmented reality and big data. So by data, we mean that we have the data recorded for the previous instances, and then based on the patterns of from the previous data. So what we are going to do, we are going to develop, let's say, machine learning models, and then we are going to implement them for uninterrupted or reduced human efforts. So that is the sort of framework for smart manufacturing and Industry 4.0. So if we look at this particular figure, then autonomous robots are very important. So be it inspection, be it inventory management, be it movement of any object from one place to another place, or for that matter, let's say if I talk about self-driving cars, they're nothing but autonomous robots. If we talk about, let's say, delivery, those drones, so they are nothing but autonomous robots. So in a sense, these autonomous robots are quite helpful if we talk about smart manufacturing and Industry 4.0. So the basic idea is we want to reduce the human effort. We want to improve the quality. So quality means when humans are working, let's say, for example, we are producing thousands of parts in a day. So it becomes very difficult to inspect and quality check each and every part. So we do sampling methods and all those things. But when robots are there, so we can improve the sampling rate, or we can improve the inspection quality. So with the help of robots, what we can do, we can increase the output and we can increase the productivity of our manufacturing industry. So from that perspective, these autonomous robots are quite important. So what we are going to is, I'll discuss a few methods of used in standard artificial intelligence for search, and then how those search methods can be implemented for navigation of an autonomous robot in an environment filled with obstacles, let's say. So that we are going to see in today's lecture. So we'll start with the standard fundamentals or concepts used in artificial intelligence. But in general, we'll talk about search methods, and based on that search method, how we are going to develop this autonomous navigating robot that we are going to see. How to develop a framework around these search methods. So that's what we are going to do in today's lecture. Okay, so you might have used these maps frequently. So just a minute. हेलो, मैं एक लेक्चर में हूँ ना, मैं देखता हूँ, मैं बात करता हूँ आपसे. Okay, so you might have used these type of maps, Google Maps, to find the routes for destinations. Now, have you ever wondered that if let's say this map is showing a way from Roorkee to Jaipur. So from Roorkee to Jaipur, it is showing almost a straight line path. So have you ever wondered that why it is showing this straight line path when you have a lot of possibilities? Lot of possibilities. What do I mean by that? So if you start from Roorkee, so there are multiple ways coming, means going out of Roorkee. One towards Haridwar, one towards Saharanpur, and one towards Muzaffarnagar, which this particular means output is following. So why did not go in this Haridwar direction? You can reach to Jaipur by going to Haridwar and then to some other random place like Bijnor and then Muradabad and then this Aligarh, then Hathras and then this Agra and then like this. So there are multiple routes possible from Roorkee to Jaipur, but why it is showing only this particular route which is sort of optimal or multiple optimal routes are being shown. So these are optimal routes. Why it is not showing any suboptimal or non-optimal kind of routes like from Patiala to Sangur and then to some Hisar to some place Hisar and then like this and this. So there are multiple solutions existing for this Roorkee to Jaipur means road, but the only optimal path is required because as a traveler, I would like to choose the optimal path. Now, this is the main framework for means the algorithm behind this search is the main framework which can be used for robot navigation also. So we'll discuss that algorithm in a while, and I'll use this example very frequently so that you can understand that what do I mean by different terminologies which I shall be using throughout the course of this lecture. Okay. So I hope by now you understand that means there are multiple possible routes, but it is showing one of the routes which is supposed to be the optimal path as a traveler, which I'll opt. Okay. So you will not opt a path which is going from Kaithal to then Sirsa and then like this. Okay. So you'll be following this particular path because this is the shortest distance or shortest time for that matter. Okay. So now going ahead. So what basically is being done over here? So there are a lot of paths, and out of which one means different paths. Out of different paths, one particular path is being searched, and that has been given as an output. Okay, so that is the framework. Now, how it is done? So what engine behind this is working? So it is nothing but a search based engine or a search engine which is working behind this particular output. So how does it work? So we are going to see that means what are the different algorithms and how does it work? How does it choose from multiple paths? Okay. So if we talk about any AI or means any optimization problem, so optimization means we have multiple ways to do to achieve the target or the goal, but we are optimizing the way to achieve that particular goal. And how do we do that? So we are having, let's say, multiple methods, and then out of those multiple methods, we are searching. So first of all, we are searching for all the methods, and then out of those all the methods, we are searching for the optimal one. So that's how the search works. So for in any means AI related problem, so search is very fundamental. So if you have, let's say, multiple solutions available, then search is very fundamental. So first of all, you need to find the solution, and then it is optimal or not. So that is to be means that is to be confirmed or that is to be logged that I am following a optimal path. Okay, so for example, like navigating a robot through a maze. So I hope you all have played those maze games which were there in the newspapers. Okay, so it's nothing but finding a path to the exit through the maze. Okay, so that is it's very much similar to a robot navigating through a unfamiliar environment. So what is working behind that? So if you can develop this particular type of problem with the help of any search-based algorithm, then you have most likely means you'll be able to solve that robot navigating problem. Okay. Now, step in this search is that we need to formulate the problem formally. What do I mean by that? So we do understand that how this maze puzzle works, okay? But how you make it means how you define this problem to a machine, to a computer, to a robot. That is nothing but formal definition of the problem. So, for example, you would have solved a lot of linear equation in matrices, okay? So, are they only to test your mathematical abilities, or are they representing any physical phenomena? So that is very important. So, means most probably that any linear problem that you would have solved is representing a physical phenomena which has been mathematically modeled in the form of equations. So that is nothing but a formal representation of a physical phenomena. And the same thing we are going to do in case of search or robot navigating problem for means we are going to define it formally so that the machine understands the problem. Now, search as the engine. So once the problem is defined, search algorithms can be used to find a solution. There can be multiple solutions out of which there are multiple algorithms. Some may yield optimal results. Some only concentrate on finding the path means to the goal state. So it depends upon the type of algorithm you are choosing. The goal of the search is to find a path from the initial state to the goal state, as I told you earlier. So now when you are when you are finding a path to the goal state, then you have to take a lot of decisions. So decision making is very crucial, and it is to be taken at every step, or I can say at every node. What do I mean by node? So for example, if you look at this particular graph, so when you start from Roorkee, so when you are in Roorkee, then you are having three ways: Haridwar to Saharanpur and to Muzaffarnagar. So you have to make a decision that which way you will be going. So whether you will be taking this Haridwar route or a Saharanpur route or this Muzaffarnagar route. So that is to be decided. So this is nothing but a decision making. So at each and every step, you are taking a decision wherever you have multiple options to select from. So for example, if you move to Muzaffarnagar, then once again you are at a node, at a junction. At that location, you need to decide that which way you will be heading to, towards Meerut or towards Bijnor or towards Sonipat, where you will head to. Okay, so at every step, at every node, what you are doing, you are taking some decisions. So which is nothing but decision making at every step. At each node in the search space, the AI agent or the robot must take a decision which state to explore next. Now, in essence, an AI agent solves a problem by searching through the space. So this is nothing but the space, search space which I'm having when I'm trying to find a route from Roorkee to Saharanpur, and then at each and every node, when I'm moving, I'm exploring that which nodes I can head to from this particular location, wherever I am in the map. So, so therefore, problem solving in AI is fundamentally a process that is driven by search. So search is very important, and then we have decision making at each and every node. So this becomes very fundamental. Okay, so this is the fundamental process of this AI and ML based methods, which we can use for various applications in, let's say, mechanical engineering. Now, search-based methods, so they treat. So what do they mean? So they treat problem solving as a process of exploring a set of possibilities to find a solution. So we have multiple ways coming out of Roorkee, and then we need to find a solution which will lead us to Jaipur. So that's so think of it like solving a maze. You don't know about the layout beforehand, so you try paths, different paths until you find the exit. So it's very much similar to that. So you're searching inside unfamiliar layout. Okay, so which is nothing but means a very similar sounding problem to a robot navigating in an unfamiliar environment. So it is taking decisions as and when it is encountering some objects or some obstacles. Now, the problem or the solution path is not immediately obvious, but we define the rules for moving from one state to another. So for example, in a maze, if you are moving in this direction, let's say in this direction, and then you can, if this is a wall, so you cannot take right because you have an obstruction over there. So the rules are completely defined. So wherever you are not having obstacles, you are moving to in that direction. So the rules are rules for moving from one state to another state are completely clearly defined. So for example, in case of Roorkee to Jaipur problem, what I have discussed. So you are traveling on the well defined roads. You're not going into the fields and you're not crossing the rivers. So this is what I mean by the rules. So you are following proper rules, transport related rules from moving from one city to another city. Okay, so that's what I mean by this well-defined rules. So example, in a puzzle problem, a route planning problem, or in a game playing problem like chess, you cannot move a pawn by 3/4 distance or 2.5 distance like horse moves. Okay, so it's quite similar to that. So you have defined rules for moving from one state to another. There are two main categories if I talk about search. So one is uninformed, that is blind search, and we have a lot of algorithms in blind search. So blind search means they don't know about means anything about the goal state. The only thing what they know is the problem definition. The problem has been defined. Now it's up to them. How do they explore the search space and then they reach to the goal. So they have no information about the goal. And the popular algorithms here are breadth first search and then depth first search. Now, there are another category is the informed or heuristic search. So it has some information or a wild guess about the goal, and then because of this heuristic or this information, it tries to optimize the path to the goal, or it tries to find out the closest path to the goal. And that becomes the very fundamental of any robot navigation problem. So you would not like to explore all the paths possible. You would like to find an optimal path which will result in higher productivity. So that's your objective without disturbing the constraints. So that you might be having some constraints that you cannot move into an object or those kind of constraints. So having followed all those constraints, you would like to reach to the goal state very in an optimal manner. Okay, so that is nothing but the case of informed or heuristic search methods. Now there are four general steps if I talk about search. So first one is goal formulation. So you know that let's say if you are developing a robot navigation approach, so you know that I'm starting from one particular state, let's say location A, and then I have to reach to a location B. So you know that you have to reach to a location B, and there you have, let's say, some work of lifting something, lifting some good, and then that good needs to be shifted to location C. Okay, so that is a next problem. So what you are going after reaching there, that is a next set of problem. But initially, you know that from A you have to reach to the goal, that is B. So for example, from Roorkee, you know that I have to reach to Jaipur. Okay, so that is my goal formulation. Now, after formulating the goal, you should formulate the problem in a formal manner so that the machine understands the problem. What do I mean by that? We will look into this particular problem formulation in detail when we'll discuss about robot navigation problem and few other problems related to search. For example, solving a 8 puzzle problem, that how we can solve that 8 puzzle problem. It is very much similar to that robot navigating problem, and we'll see in a while. Then after formulating the problem, the important thing is that you need to search from the different uh, possible routes. That means a robot can navigate from location A to location B by several different routes possible. But then which route, the means what is your objective? Whether you need to find the optimal path or just you want to reach from location A to B. So depending upon that, you will have to search, you will have to opt from different algorithms which are available. Okay, so the search algorithm takes a problem as input and returns a solution in the form of an action sequence. So, for example, from Roorkee to Jaipur, you're not reaching to that location Jaipur directly. It is not directly connected with Roorkee in a single straight line fashion. So you have to navigate through different locations like Muzaffarnagar, then Meerut, then you have to cross the NE2, then NE4, and then so there are a lot of nodes or sequence of action which you will have to follow to reach to Jaipur from Roorkee. So similar to that, what search will give you? Search will give you different sequence of actions and out of which you can select the optimal one, or if the algorithm is designed in such a manner that it is directly giving you an optimal solution like Google Maps gives you, so then it is fine. So you can directly follow that particular route or you can directly follow that particular solution. Now once you have found out this means a route, then what you are going to do, the next thing is you're going to execute. So these are the 4 steps. So first is formulate, be it problem formulation or goal formulation, and then you are going to search, and then you are going to execute. So if we talk about, let's say, any AI based application development for any process, not it's not about the robot navigation problem. It is one such problem which we can definitely solve with the help of this search methods. So what we are going to do, we are going to formulate the problem formally. Then we are going to search for the solution, and then we are, after searching and finding the solution, we are going to execute that. So we'll see with the help of a short video that how this means robot navigation problem is being formulated, and then a possible path is being searched, and then it is being executed. Now, if we talk about, let's say, problem formulation, this is a very first and crucial step. If we talk, if we talk, means if we consider, let's say, any problem which is to be solved with the help of these search-based methods. So, for example, let's talk about a 8 puzzle problem. I hope you all know that what do I means, how does a 8 puzzle problem looks like. So it simply looks something like this. So let's say this is the initial state, and what you are supposed to do, you are supposed to arrange all these. So this is a 3 by 3 or 9 grid matrix, and then here you have 1 2 3 numbers written up to 8, and one space is kept blank, so that, and the goal is to arrange these alphabets in a particular fashion. For example, it can be 1 2 3 4 5 6 7 8, and you want the blank in the middle. So that can be a one that can be defined as one of the goal state, or it can be 1 2 3 4 5 6 7 8. You can keep the blank at this ninth location. That can be another goal state. Okay, so depending upon the rules of the game, you can define a particular goal state, and you're starting from this initial state. So the initial state is very important. For example, if I'm starting in Roorkee, then I'll consider the Roorkee as the initial state, and what all options do I have. So if I'm starting from Delhi, then Delhi becomes my initial state if I'm heading towards Jaipur. So what all possible routes I do have from Delhi, or in case of Roorkee, what all possible routes I have, or means ways do I have from Roorkee. So initial state, defining the initial state becomes very important when you start navigating this search space. Then you need to define the possible actions, the all set of possible actions. For example, here in this particular case, what I can do, this is the position of blank. I can move this blank up, I can move this blank down, and I can move this blank towards my right. I cannot move this blank towards the left. But had this blank been in the center, then what all possible actions were available to me? So moving up, down, left, and right. So all those 4 possible actions were available to me. So in general, for this 8 puzzle problem, how many possible actions do I have? I have 4 possible actions, but for a particular state, we may have only means 2 out of these 4, or 3 out of these 4 actions available. So for example, in this particular initial state, I have only 3 actions to carry out. So up, down, and then right. There is no left motion possible of this blank, because this is the limit. So we need to define all these possible actions. So the first thing is that we are describing the initial state, and then we are deciding when then we are finalizing the possible actions, and then at that particular state, what are the possible actions or applicable actions. For example, when I am in Delhi, so I have a way towards Roorkee, and then a way towards Jaipur, and then a random way towards, let's say, Sonipat or Chandigarh. So at Delhi, I'm having different applicable actions, and at Roorkee, I'm having some different applicable actions. So this is this is you need to define. So for example, in case of robot navigation problem, you can define the robot can move in perpendicular directions like north, south, east, and west. Only these directions are possible. Okay, so it cannot move in northeast direction or north west direction. So those kind of rules you can frame that how the navigation is possible in the search space or in the navigation environment. Okay, so this is how means you are defining the problem, that how a navigation problem is to be solved. Then if you have defined the actions, then what do you have? You have so when you apply all these actions at a particular state, then you will be getting the transition state. So for example, if I move this blank towards the right, so what I'm getting a different state that is nothing but S star. And this becomes my state, means space, search space. Okay, so if I apply all these possible actions at the initial state, and then if I reach to that, let's say this particular state, and then from this state, if I once again apply the applicable actions up, down, left, right, then I'll be having, let's say, 4 sub branches. So likewise, what I can do, I can expand from this initial state to the goal state through different paths. And what do I mean by that? I simply mean this. So for example, this is my initial state, that is nothing but my root node. So what I'm trying to do, I'm trying to create the search space. So for example, in case of Roorkee to Jaipur problem, I am starting from Roorkee, and then I can go to Haridwar, Saharanpur, to Muzaffarnagar. So likewise, I'm finding out different ways possible. And out of those ways, which way I'll be selecting, that depends upon my algorithm, which algorithm I'm choosing. Okay, so for example, in this particular case, you have this root node, which is nothing but your initial node, and then up, right, down, left. So if you are moving this space up, you're getting this particular state, and then if you're moving this right, then you're getting this state. If you're moving it down, then you're getting this state, and then when you're moving it left, you're getting this state. So these are the applicable actions at this particular node, and then these are the resultant states. And out of these resultant states, once again, if I'm applying the actions over here, so I'm getting these 2 states. So for example, it can be moved towards, this blank can be moved towards left, towards right, and then to down. But as we came from this down orientation earlier, so we are not considering once again going back to the parent. So these all 4 nodes are called the child nodes, and this is the root node. Okay, and these branches are nothing but they are the actions or applicable actions at this particular node. And this whole representation is called search tree or state space. Okay, so this is in the form of tree, and this I have developed with the help of defined actions, like in case of this 8 puzzle problem. So I can then means after this, let's say these 2 actions are possible, and then at this particular state, if you look at, so only one possible action is there. I cannot go back to the parent, like I cannot move this space to this this blank to this location of 1. Otherwise, means in this particular case, I'll be going back to my parent. So I don't allow going back to the parents. So what I can do, I can move this down. So by moving this down, so only one applicable action is available at this particular state. And likewise, what I'm doing, I'm trying to develop this whole tree until and unless I find the goal nodes. And the moment I find goal nodes, and then I look for the optimal or any path which I can follow to reach to the goal state. Now, whether the path is optimal or not, that will depend upon how you are selecting out of the childs. For example, let's say after 5 passes down this section, I'll reach to the goal state. But if I opt for, let's say, this section, then I'll have to go down to 10 steps to reach to the goal state. So this branch is not an optimal, is not giving you an optimal solution. Rather, this branch is giving you an optimal solution. And then how which algorithm you are choosing such that you are reaching to the goal state in an optimal manner, that is a different thing. So it's like, means we have different possible routes from Roorkee, and then we have means we have expanded in the form of tree that which all possible routes are there to reach to Jaipur. So, and now once this tree or search tree is defined or is framed, then we can go for search. So we can go for searching for the path. Okay. Now, so when I'm generating these nodes or child nodes, so this is called search tree. So whenever I'm generating these child nodes from a parent, then what I'm doing, I'm just doing a goal test. So whether this state, whatever state I'm reaching, let's say from this means from this particular parent, I'm going to get these two childs. So whether these childs are my goal state or not, that we are going to see. Okay, so we are going to perform a goal test. So whether we have reached to the goal or not. So if we have reached to the goal, then we would stop the algorithm then and there itself, and then we'll find a path, and then we'll try to follow that particular path. Okay, so this is nothing but the goal test. So at each and every node generation, what I'm doing a goal test, and then that goal test, with the help of that goal test, I'm just looking that whether I have found the solution or not. If, let's say, this is my goal state as I defined earlier. So 1, 2, 3, 4, 5, 6, 7, 8, and the blank is at this particular location. So if I define this as my goal state, the moment I reach to this goal state in this search tree, I would say that, okay, so I have found a solution and this is the path to the solution, and this can be followed to reach to this particular goal state. Okay, and this is nothing but solution, one of the solutions, possible solutions. Whether it is optimal or it is suboptimal, that depends upon the type of algorithm what we are choosing, and we'll see in a while that what kind of algorithms do we have. So now this goal state for the 8 puzzle problem may appear for multiple instances in a search tree. So for example, I can follow this particular route and then I can reach to the goal state, or I can follow this particular. So multiple ways are there to reach to this particular goal state. Okay, so this is, for example, which I discussed about that Roorkee Jaipur problem. So I'll discuss about that problem very frequently. So it means that we have multiple ways possible to reach to Jaipur, and which route is optimal, that depends upon the type of algorithm, whether the algorithm is giving you an optimal route or not. Okay. Now, if we talk about optimality, we need to define a function which takes care of this optimality. So we define a path cost. So for example, in case of, let's say, 8 puzzle problem, every step is a cost. So you can take account of those steps, how many steps you have taken to reach to the goal state. For example, one player is reaching to the goal state after 10 steps, and you are smart enough to reach to the goal state in 5 steps only. Okay, so then your cost or your path cost becomes optimal, or your solution becomes an optimal one. Okay, it may be a suboptimal, but in comparison to the other fellow, you have found a better solution. I would say not optimal, but better solution. Okay. So for that, we can define this path cost. For example, in case of Roorkee to Jaipur problem, if you are reaching to Jaipur on the path shown, so it is, let's say, it is giving you less kilometers. And if you follow a path from Haridwar to some other location, and then it may give you, means you have to travel more kilometers. Okay, so that is nothing but the path cost defined in terms of kilometers. So it can be any parameter. For example, in a robot navigation problem, if productivity is important, so I would define that how much time it is taking if the speed is constant. So how much time does it taking to reach to the location? So that becomes very important if productivity is important. So we can define the path cost in terms of kilometers, in terms of steps taken, in terms of time taken. So it depends upon us that how do we define this path cost. Now, this is a problem formulation for this is a very common problem you will find in various videos. It has been discussed in the book of Norvig, if you follow. So here, what is the goal? The goal is to means a person is traveling in Romania, and then he needs to reach to Bucharest from Arad, and he is having let's say flight to board from Bucharest, and then the objective is to reach to the Bucharest in shortest possible time or with shortest means with minimal efforts. So that is the aim. Now it's a very similar problem to what we have defined from Roorkee to Jaipur. So it can go to different locations like this, and this, or it can follow a very optimal path like Sibiu, Fagares, and then Bucharest. Okay, so but how do you define this problem? So that becomes very important. So we are not talking in terms of coding, but formal definition, how it can be defined. So the initial state, if you see, so where the agent is starting, it is starting in Arad. So it is starting in this city of Arad. And then it's an abstract mathematical model. Means we are not defining what is the temperature, what is the weather condition, what is means what are his or her fellow companions or travelers. So we are not defining all those things. These are abstract information. So we are only defining that this is the important information which can be used in problem formulation. And then if we talk about, let's say, actions, so the first thing is initial state. The goal formulation is finalized in the early step itself, that the goal is to reach to Bucharest. Then the initial state is defined like Arad in Arad. And then the actions, what all actions do we have from Arad? It can go to Zerin, it can go to Sibiu, and it can go to Timisoara. So three possible actions are there. So these are nothing but possible actions. So if you remember that in 8 puzzle problem, so we have possible actions up, down, left, right. Similar to that, we have in this traveling problem, which is very much similar to a robot navigation problem. So slowly we are linking this search theory with the robot navigation problem. Just try to understand. So from Arad to Zerin to Sibiu to Timisoara, so we are moving in different directions. Okay, so we can move in different directions. The transition models, what it gives. So if you are in Arad, then if you are in Arad and then if you go to Zerin, so then what will be your transition? So you will be in Zerin. So if you are traveling to Zerin, so the next state will be that the agent will be in Zerin. So from Zerin, let's say if it goes to, let's say, Oradea is this place. So then the transition state will be that it will reach to the Oradea. So likewise, we can create a different the search tree for this particular problem. Okay, so we'll see that how it is created. And then agent's goal in Romania is a single. So the goal is single. Goal is to reach to Bucharest. And the step cost for Romania, so the step cost, maybe these step costs are written over here. So let's say 151 is the cost, or it may be the time, or it may be the distance in kilometers from Aradia to Sibiu, or let's say from Arad to Zerin, it is 75. From Zerin to Aradia, it is 71. So it can be anything. It can be kilometers, it can be time, or it can be something else, depending upon the performance parameters defined for this particular problem. For example, the steps, what we have defined in case of 8 puzzle problems, that is nothing but your cost. Okay. So this is how this problem can be defined. If you can see that we have to move from this. So this is the formal definition or problem formulation for this particular simple traveling problem. So now how it is to be solved, how it is to be looked into with the help of different algorithms, that we are going to see in the upcoming slides. Now, one very similar example means the earlier problem was from moving one city to another city, and we had certain actions like the agent can move to different cities, connecting cities. Okay, So for example, this is a robotic assembly, if you can see, and the objective means that the aim is to do assembly for, let's say, multiple parts. And now what all degree of freedoms available. So these are nothing but so the actions, what all actions available at my end to perform. So that is nothing but the different degrees of freedom available to me at this particular location. So this is one particular state. This the location, exact configuration of this robot is one particular state. So if I do anything, let's say if I rotate the front arm, so it has changed its state. So this is one action which I can take right now at this location, and then I can move to different state. So likewise, what I can do, I can create multiple states. So I can define that this front arm can rotate from, let's say, this configuration to 90 this side and 90 this side. So it will be covering all the possible actions. So I have defined that 90 from this particular state, it can move 90 this side and then 90 this side in a graduation of, let's say, 1 degree. So I have defined those states for that particular arm. And for example, for another instance, let's say this arm can slide inside this hollow space. So I can define that it can slide. So from this state, it can slide, let's say 50 mm this side and 50 mm this side. So that's one more thing what I have defined, that what all states are possible. Okay. And this can also be done, let's say, in the step of 1 mm or so. And then we have this arm which can rotate along this, and then this arm can rotate along this. So if you can observe that we have multiple degrees of freedom and multiple states are possible. Now, compared to previous problem, which is nothing but the problem of moving from Arad to Bucharest, we had at this particular location, we had three options possible: going to Zerin, going to Sibiu, going to Timisoara. Now, compared to this problem, if you can appreciate that the complexity is significant over here. It is a very complex and means lot of variables are there to consider. From means or in other words, if I would like to say that there are a lot of states possible from this particular state itself. So it's a very complex problem in that manner. And now what I need to what I need to find out, I need to find out those possible actions, those possible motions which give me the final assembly, or let's say a one weld which I'm targeting. Okay, so I need to move all these joints in such a manner that I achieve a welding configuration, or for that matter, as shown in this particular figure, I just want to do some assembly. Okay, so this is how this problem can be defined. This is a very complex problem. We are not going into solving this problem. It is beyond the scope of this 2-hour lecture. But just to give you a feel that how this search problem is related to a problem of robot navigation or assembly line problem. Okay, so it can be solved. And then means what algorithm we are using, depending upon that, we can get an optimal solution. Okay, so now if I try to define this, so set of states, what set of states means, I'm formulating that tree, space tree. So coordinated and angles of robotic joints, parts of object which is to be assembled. So those all becomes the set of states. Okay. And then initial state, any configuration of robot and object parts. So these are the parts which are to be assembled, and any configuration of this particular robot becomes my initial state. And then operations and actions. What are the actions available, applicable? So continuous motion of robot joints. So I have shown you that you can rotate this on this axis, and then this can be rotated on this axis. So these becomes my operations or actions from this particular state. So the state space or the tree, search tree, will be huge in this particular case. Okay. Now goal test, the goal becomes my the complete assembly. So the moment I find that particular configuration, it means that I have done, or I have found a path. Whether the path is optimal or not, that is a different thing to look after. And then path cost, what can be the path cost? So it can be the time to execute this particular assembly. So this should be minimum. Okay, so that defines my optimality, whether the path found out is optimal or not. Okay, so now how do we define these nodes and all? So that is nothing but given means I'll not discuss this in detail, but yeah, this is how this data structure for a particular node is defined. So it typically contains five components. One is state. The state means in which to which the node corresponds, and then the parent from which state it is coming. Let's say it is, so in this example, if we talk about, so let's say this is one state. So this is means if the agent moves from, let's say, array to CPU, so then the CPU is the current state and the parent is array, so it is coming from array. So likewise, we are defining this particular node. So when agent has moved from array to CPU, then what would be the node or the data structure for that node that is required for programming. Okay, so when you do write a program, then these things are to be defined particularly so that it can differentiate from different nodes. Okay, so the basic purpose of this is that. Okay, what actions you have chosen from parent to reach to the current state, and then what path cost is there. So for example, in this particular case, this is the path cost, which is 140, and the action is you have moved from array to CPU, and then this is the current state, the parent is array, and then path cost is 140 in that case, and then heuristic cost is nothing but you have some information about the goal. So that is nothing but heuristic. So as I told earlier that we have different algorithms where some algorithms are not having any idea of the goal, but there are some algorithms which keep a very basic or rough idea about the goal state. So that is nothing but a heuristic information, okay, or inform. Now this fifth component, if you can see, so that is heuristic cost is essential for informed search, as I told you. So like A star, which is typically the engine or the search algorithm behind this Google Maps. So it works on the on this A star algorithm. Okay, so which evaluates nodes by combining the path cost and the heuristic cost. What does it mean? So we'll discuss in a while. Okay, so now this is how the state space looks like on a graph. But if we try to develop this on a tree, then it will look very much similar to the 8 puzzle problem that we have discussed earlier. So this is nothing but the tree representation that from array you are starting, you are reaching to CPU, Temisora, and Zerit. This is how means we define this. So now we are moving towards solving the problem. So we have once we have formulated the problem, so now we are moving towards visualizing the problem, search problem after formulating it. And then we are trying to see that how it can be represented in the form of tree. So let's say if we start from array, then I can go to Cebu, Temisora, and Zerin. So if you can see over here, so from array, three possible actions are there, like we had from Roorkee, from to Haridwar, to Saharanpur, and to Muzaffarnagar. Similarly, from array, you can move to Zerin, to Cebu, to Temisora. Okay. So these three possibilities are there. And then let's say you are trying to explore this CBU, that how you are going from this CBU. So if you have no idea about the goal state, then what you will do, randomly you will pick one of the nodes out of these three nodes, and then you will try to explore those nodes. And then once again, randomly you will pick out of the expanded nodes, and then you will expand all those nodes. So for example, let's say randomly you picked Cebu. You have no idea about the goal state. You have randomly picked Cebu, and then from Cebu, once again you can go back to array because it's a bidirectional problem. So from Cebu, once again you can go back to array. So that all that is a possibility. And then apart from that, you can go to Fagares, Oradia, and Reminiku Vilcia. So if you see this problem, so from array to Cebu, and from Cebu, you can go back to array, you can go back to Oradia, not go back, but you can go to Oradia, you can go to Fagares, you can go to Reminiku Vilcia. So these all possibilities are there from Cebu. That's how you're going to define, you are going to prepare your search tree the way we did in case of that 8 puzzle problem. So now there are certain things when you solve these kind of search related problems, you would like to keep in mind. So what are they? So the nodes which you have explored or visited, you will mark them as explored or visited. So you can see that these gray shaded nodes, these are nothing but the nodes which have been explored or they have been visited. So you may put a condition that whatever nodes I have visited, I'll not be visiting them again. So for example, from CPU to array, you can go back, but you have already explored the node array. So if you develop the algorithm in such a manner, if you write a code in such a manner that you are avoiding the explored and visited nodes, so in that case, you will not go back from CPU, you will not opt this path to go back to array. And that will save you from going into a loop. Because otherwise, if you don't put that condition that you will be ignoring the explored and visited nodes, if you don't put that condition in the program, then what it will do, it does not know. It's a machine. It does not know that you have reached to array once again. Okay. The only thing how it knows that it will be comparing this array to some set which is nothing but explored or visited set. And if it finds that this array is already there, then it will not go into this particular node. So otherwise, what will happen? So it can go from array to CPU, then CPU to array, and then once again array to CPU, then CPU to array. So it can go indefinitely into a loop. So it can go into an infinite path. So this explored and visited set you are keeping, and you are just comparing that whatever node you are picking for exploration, is it explored, already explored? If it is not explored, then only you are going to explore it. Okay, so you are keeping a check of these explored and visited nodes. Then you have frontier and fringe. Frontier and fringe are those nodes which are available for exploration or which have some nodes or some connections to explore further. For example, if you talk about, let's say, Fagares, this array is already there in the explored or visited nodes, for example. Then if you have, let's say, this Fagares or let's say this Timisora, it is, so all the frontier and fringe nodes are represented in white color. So you can see this, these all white nodes are in frontier and fringe. Means one is same name, different terms. Same thing, different terms. So if you see this Temesora, then you can go to Arad and you can go to Lugos. So it has some ways to explore. Okay, so these are nothing but these type of nodes are called frontier or fringe. Okay, and then these are my unexplored nodes. So at this moment, when I have this frontier and these logos already are, so these are nothing but my unexplored nodes. And if any node is terminating, it is not having any way possible. For example, this Niamt, if you can see, so from this particular node, you don't have any node connecting to this. So this will be called as the leaf node. So you can see that this will be, wherever it will occur in this search space, so it will be called as leaf node. It is not having any way to be explored further. Okay, so this will be called as the leaf node. So these are nothing but these are some terminologies which you will find very helpful when you are writing a code, because ultimately when you are defining this, when you are finding a robot navigation problem, you need to see that you are not retracing the path back. Okay, for that you will have to in the program itself you will have to write that if you have explored that particular location earlier or not, that you need to remember. Okay, and for that matter you are maintaining these data sets. Okay, now so this is regarding how you formulate the problem, and now we'll see some search methods which can be used for let's say for this particular problem itself. So for this particular problem of traveling from Arad to Bucharest. Okay, which is nothing but very similar to a robot navigation problem. Okay. So I told you that there are different search strategies. Like one is this uninformed or blind search. So in this uninformed and blind search, we are having these primary algorithms. One is breadth first search, depth first search, and then you have uniform cross search. So we'll be discussing them in a very brief manner. I'll not miss because of the time limitation. I'll not be going into the details of this, but these are very interesting topics to study. So if you are having any interest, so you can go. And it's not about the robot navigation problem only. You can solve multitude of mechanical related problem, mechanical manufacturing related problem with the help of these algorithms. This is the beauty of these algorithms. Okay. So we'll be seeing. So what is the primary condition in uninformed and blind search? That apart from that problem formulation, whatever we have done, so they have no prior knowledge about the goal. So they only know that how you can move from this state to the neighboring states. Only the child, how they can explore. So this is the only information how they can explore the childs, and then means how the childs of childs are being explored. So that depends upon that which algorithm we are choosing. So for example, in case of breadth first search, we'll see that how does it progress. So breadth first search, it's a very simple strategies. So what it does, it tries to keep the search space very close to the initial state, or it will try to search the space very close to the initial state. Or this means, for example, if I'm trying to find out, let's say, way from Roorkee, or so for example, this problem. So Arad to Bucharest. So what did it do? It will try to explore the nearest possible locations first. So all the nearest locations first will be explored. So for example, till this point, it will explore all the locations and then it will reach to Bucharest. Okay, so this is how it does, and how it is doing. So it does by maintaining a queue that is a first in first out. FIFO based queue is maintained, and then it gives you the solution which may be optimal if you are considering, let's say, number of stops, but it may not be optimal in terms of distance or time taken. Okay, so number of hops or number of stops will be very few in case of this breadth first search. And how does it work? So for example, I have prepared a tree from that graph or from the applicable actions. Let's say transition model I have applied, and then I have created this node. So I'm starting, let's say, from initial node A, and then what do I have? If I explore, so I can go to from A, I can go to node B to node C. So it is very much similar to this particular problem. So from Arad, I can go to Sibiu, I can go to Timisoara, I can go to Zurich. Okay. So this is how I can go to from A to B and C. Then I'll explore the B first. It will give me, so all the shaded nodes, gray shaded nodes are the nodes which have been explored. Okay. Now just remember the fashion in which it is being explored. So initial node is A. Once it is explored, it is marked as gray. And then we have white nodes, which are nothing but your frontier and fringe. So once you explore this B, you are marking it gray. So then after B, you open this C. So after means when you were exploring A, so B was open, B was explored, and B was opened, and then C was opened. So B has been explored here, and now it's turn of C. So C is being explored. So for B, we have found that D and E are childs, and for C, F and G are childs. So we have not opened them up. We have only found that for C, the childs are F and G. Similarly, when B was explored, so D and E, they were opened. They were not explored. They were only opened and kept in the frontier list. And from the frontier list, I picked now C, and then C was opened in F and G. Now it's a turn of this D. So this D will be explored, and then its children will be marked. From E, where we can go, so those will be marked. So so it starts in a fashion that this level is being explored first, then this level is being explored next, and then this level is being explored next. So it is always keeping close to the search, means to the initial state. So this manner it is exploring. So let's say once again, if we have, let's say D is having means two more children, then E is having two more children. So all those children will be explored next, and then further the children of the successive nodes will be explored next. So in this manner it is exploring. So this is nothing but your breadth first. So you are exploring a breadth first, and then you are going to the next breadth possible. So this is how it explores. Okay. Now, for example, this is my search tree, and I can reach to B and C. And in this search tree, I have multiple goal locations. So for example, if you can correlate this with eight puzzle problem. So you can see that these are all possible goal nodes, which I can reach from different paths. Okay, so one is this path, one is A, C, D, F, G. This path, one is A, B, D, F, G. Another one is A, B, D, P, G. So these are different paths with the help of which I can reach to these goal state. Now, breadth first search, how it will do, it will try to keep the search near to the initial state. So it will explore this, then it will explore this. The moment it explores, let's say B, it will open D and E. The moment it explores C, it will open D and G, and you'll get the goal node here itself. Okay, so the path is A, C, and G. So it is finding out this particular path. So this is how a breadth first search proceeds. Okay, so we have not gone into the details that how this how the program is to be written for that. So that means if you are having an interest in this, then you can, or depending upon the specific problem, you can go and try for writing the program for the particular problem which you are interested in. But the idea is that it is exploring in the breadth manner. So first breadth, so initial depth is explored, then the next breadth is explored, then the next breadth is explored. This is how it is being explored. So it is not reaching to these goal state. And in a sense, it gives you a path which is having less number of stops. Only one stop is there. Or if we talk about, let's say, 8 puzzle problems, so only 1 and 2 step solution it is giving. Okay, so it is, so in case of uniform path cost, it will give you an optimal solution. But in case of the path cost is not uniform, it may be an optimal solution or it may not be an optimal solution. Fine. So now this is the path which has been explored. So A, C, and G. So this is my goal node. Okay. And now let us look at depth first search. So the one method of blind search is breadth first search. The other method is depth first search. So how do we do this? So as the name suggests, so it will deep dive into the first depth, first leg. And how do we do that? It uses a data structure of stack, that is last in and first out. In the breadth first search, it was using first in, first out, FIFO based queue, but here it is using a data structure, stack type of data structure, that is last in, first out. So if you would have, if you have any exposure of C and C++, if you have read those kind of data means structure, so you might be familiar with this, how this stack works or how this queue works. Okay. So stack works very similar to the stack of those CDs. Okay. So the last CD which you are inserting, it needs to be ejected out first. Okay. And the queue works in a fashion which is typically we find at many places. One such example is the railway ticket counters. Okay. Nowadays, nobody is visiting railway ticket counters, but because of these online platforms. But yeah, all of us might be having an idea that how the queue works there. So in this stack manner, so what it does, it explores. So from the initial state A, it goes to B and C. Then it explores B. B gives you the child, that is D and E. Then it explores the first child of B, that is D. Then it gives you P and F. Then it explores the first child of the previous parent, that is P, and then it gives you G. So it is straight away dives into this particular path, and that is my depth first search, how it works. So the same tree, what we have explored with the help of BFS, but here you can see that the path cost, if this is a uniform path cost, let's say in exam means in case of 8 puzzle problem, it's a uniform path cost. One step counts to one path. So here you can see that it is means it is reaching to this particular goal node. So in a sense that in a sense it has found the path to the goal state, but it may not be an optimal one. Okay. So we have seen that this is the optimal path if the cost is uniform. Okay. So this is how this depth first search works. Okay. So for example, this is the path, or the algorithm returns the path A, B, D, P, G. A, B, D, P, G. This is the path what I have found. Now, if I compare these two methods like BFS and DFS, so there must be some differences. For example, if this is the representation of BFS, this is the representation of DFS. Now, if you look at this particular thing, so this is my start node and this is my goal node. I have to reach this. I told you that BFS works in a manner that it looks for all possible solutions near to the initial state. So it will explore the whole search space like this, and then it will move from this to this, and then it will find this. So it will take a lot of time to explore all these nodes, which are not goals. And that's a very fundamental issue with these blind search methods. It is unnecessarily exploring all the nodes. Can we optimize this problem so that directly we can reach to this particular goal node by exploring these nodes as quickly as possible? Because in case of robot navigation, you would like to find a path very quickly. That defines the productivity, isn't it? So this is how this BFS works. And if you look at this DFS, it is quite random. Quite random in the sense means you can see over here it is started from this, and then it dive deep into this particular path, and then it is moving in this manner. So it is moving along the depth. Okay, so once it explores this, and then it will go this, and then it will go this. So likewise, it will circulate, and then it will reach to this goal node. So the manner in which you are exploring these nodes is also important. So instead of exploring in this direction, you can start exploring in this direction, and then you can directly reach to this particular goal node. So it's quite random. So there is no information about the goal in the start of the algorithm. So it's quite random. So you may end up along this particular path which has been shown into this particular figure, or you may end up getting a path which is very optimal in case of DFS. For example, if we talk about, let's say, this particular example, so if you explore the nodes in a manner that you keep C over here instead of B, so C is being explored. Okay, so because you are opening B and C, let's say if you open C and B, so if you are keeping C here, then this child of C, that is nothing but this G, will be explored first. Okay, so it's quite random. So the idea is to compare the performance, or to see, to visualize that how these both algorithms are working. So this is how these two algorithms work, and they are not very popular for robot navigation problem, or the navigation problem which is being used by this Google Maps. Okay, because it may take a lot of time. So if you are running, let's say if you are finding the path from Roorkee to Delhi, or Roorkee to, let's say, Indore, so it will explore all the BFS will explore all the possible routes toward close to the Roorkee first, and then it will reach to the Indore. Whereas this DFS may go in, let's say, northeast direction first, and then after exploring all the options, it will come, and then it will search for other parts of the map. So in that sense, they are not very optimal. We need an optimal algorithm to solve that problem of robot navigation. Okay. So another search method is uniform cost search. It is sort of a heuristic, not heuristic about the goal state, but yeah, the path what we have traveled is being used. So whatever path we have traveled, so it keeps a track of that, and in a sense, it tries to optimize the the path. Okay, so how does it do? So it keeps a track of minimum means it keeps a track of this cumulative cost and it tries to keep this cost as minimum as possible. And that's how it explores the node. For example, this particular problem, if you see, we are starting from source and then this is the destination, which is possible from two routes. One is from source to B, E, F, G, and then destination. This is just a simple robot navigation problem. So you can have multiple paths emanating from this source to this goal. And then you have different, so this is, let's say, the time taken to travel from B to E, E to F. These are the time taken which are written over here. So if you see this, then this is the destination. So now you have to find out that which is my optimal path. So this is my evaluation function, which I was talking about. So this evaluation function is being calculated. So here you can see that this is my evaluation function Fn. And then this is Gn, which is nothing but my path cost. So from source to B, what is my path cost? Here it is 3. From source to C, what is my path cost? It is 1. And then we have this Hn. Hn is nothing but the heuristic cost, as I have already discussed in the previous slide. This Hn is nothing but your heuristic cost. So this Hn we are not utilizing here because it is a uniform cost search method and another blind search method. It is blind in the sense that it does not have this heuristic, or this heuristic tells you about the goal. Okay, so it is not having any information about the goal, but rather it is utilizing that what distance I have traveled. So let's say if I start from Roorkee, then to Haridwar, to Saharanpur, to Muzaffarnagar, how much distance I have traveled. So when I'm reaching to Haridwar, how much distance I have traveled. So if I see that the distance to Muzaffarnagar is less as compared to the next other two stops, so I'll start proceeding in Muzaffarnagar direction. So that's how I will be proceeding. So it only has the information of the path traveled. So for example, source to B, I have moved and it took 3 minutes time. Source to C, I moved and it took 1 minute time. Okay, so that information I have after traveling, how much time it has taken. So that information is there. This is nothing but the path cost. And now if I try to solve this problem with the help of this GN, then I will maintain a priority queue. Priority queue means I will be having these GN functions for different nodes. And then whosoever is having this less GN, that node will be explored first. So that node will be given the priority to be explored first. Okay. So in that sense, it is also based on a queue, but it's a modified form of queue, that is priority queue. Some weights are given to different nodes, and based on those weights, the nodes are being explored. So for example, if you see this is the source, we are starting with this at this particular location. So time taken or this score is or this GN path cost is 0 when we are starting at source. And then when we explored the nearest node, that is A, B, C, we found that to reach C, it is taking 1 unit of time. So I'll be interested in exploring this one rather than this A and B, which is having path cost of 2 and 3 respectively. So when I explore this C, then I reach to F. Now the total cumulative time taken to reach F is 7. And now if it is 7, so I will look into other nodes available in the queue. So I had 2 already available, 3 already available. 1 I have explored, I have reached to 7. It's F. So now I will see, I'll compare this time taken, cumulative time for different nodes which are available to be explored at this particular point. So this A is available, B is available, F is available. So 2 is the minimum cost at this node A. So I would rather explore this node compared to B and F. So let's explore this node A. So the moment I explore A, I reach D. It is having the cumulative cost of 4. Now I'll compare this cumulative cost with other available nodes for exploration. So B is available at 3. And then F is available at 7. So what I'll do, I'll explore the B next. So the moment I explore B, I reach to E. And at E, I'm getting this path cost, cumulative path cost, that is from source to B to E. This is cumulative cost, 3 plus 1, 4. Similarly, 2 plus 2, here it is 4. So now I have 3 nodes for exploration, and the cumulative cost for 3 nodes is 4 for D, 4 for E, and 7 for F. So both of these nodes are having a type, and any one of them can be opened, or they both can be opened simultaneously. That's not an issue. Or we'll see that if you open one by one, then both will be opened sequentially. The moment I open E, so it leads to F, which is nothing but 8. And then this 4 is the least cumulative cost. So I open this 4, I reach to 7. So in the similar fashion, if I expand, so 7, 7, 8, so I can expand either this or either this. So if I expand, let's say P, I reach to Q. Q is 9, F is 8, this F is 7. So if I expand this F, which is 7, so I get this 8, 9, and 12. If I expand this F, I reach to G, G is 13. So now I have 9. Q is 9, but the Q is not leading to anywhere. It is terminating. So it's a dead end. Now what do I have? I have this 12 and 13. So I'll be exploring this 12 because 13 is higher. So 12 will be explored, and 12 leads me to the destination 19. But still I have a node which is open and it is having a 13. So from G to destination, if I have a path which is giving me a value less than 19, then I'll explore it. Otherwise, 19 is my final optimal path. Okay, so this is giving me the optimal path. It is not optimal in the sense because it is not keeping the track of that how far is my destination. It is only keeping the track of how much distance I have traveled. Okay. Now, so these are the methods which are based on uninformed search methods. So let's dive deep. Let's have a idea about the heuristic search strategies or search methods, which are typically used in case of robot navigation type of problems. Okay. So first one is greedy best first search. So what it does, it only has the idea about this. So out of this, the evaluation function here looks something like HN. So it has the idea, it has a guess about the location or the distance towards the goal state. Okay, so it does not keep track of the path cost which has been traveled. Okay, the path which has been traveled. So it only looks for this HN. So HN is nothing but an estimated cost of the cheapest path from state at node N to a goal state. Okay. So notice that HN takes a node as input and it depends only on the state at that node. So let's say if we have reached from RR to CBU, so it will not keep track of the distance what you have traveled from RR to CBU. It will only keep track of from CBU how far is Bucharest or how far is the goal state. Okay, so from that node where you are present currently, from that how far is the goal state, that will be considered. Okay. Whereas in case of another algorithm is a very popular algorithm which is being used in this Google Maps. That is nothing but A star, and which we'll also be using for robot navigation problem. So A star is another algorithm. So here you can see that the evaluation function for A star is Fn equals to Gn plus Hn. So it keeps a track of this path cost and this estimator heuristic function as well. So we'll see that how this problem of reaching from Arad to Bucharest can be solved. Now we need a heuristic. So in the map, if you have seen that Google Maps, so what I can find out this straight line distance from Roorkee to Jaipur. That becomes my best heuristic or best guess. Now what I'll do, I'll just try to move in that direction where the total travel distance and the estimated cost or this evaluation function is very close to this straight line. That's what I'm trying to do basically in case of A star. In case of greedy first, I just look at this distance. So from Arad, it is 366. From Arad, we have 3 possible combinations. That is Sibiu, Timisoara, and then one more, that is Zerid. Okay, so this is the evaluation function for your that algorithm, which is greedy best first search. Okay. So let's see if on the basis of these distances only, what route we are able to find out. So let's say we start from array, and then from array we have three possible combinations or routes. From array, the HN is 366. And then from array, once we open this Sibiu, Timisoara, and then Zerin. So what are the straight line distance from Sibiu to Bucharest? It is 253. From Timisoara to Bucharest, it is 329. From Zerin to Bucharest, it is 374. So out of these three nodes, which one is having the least straight line distance? So the Sibiu is having the least straight line distance. So I'll pick this and then I will. So it is not considering the cost or the path what you have traveled to Sibiu. It is started from Arad. So Arad Bucharest is somewhere here. Okay. So it is started from Arad. It opened the possibilities, and from Sibiu it is looking. Then once again it is seeing that how much distance is left from Sibiu, straight line distance. So only heuristic function it is considering. Okay. So that HN or this HN is only being considered. Okay. So once I open this Sibiu, what I get? I get these possible options. This is array. Once again, I can go back to array. So here, if even if I keep these parents, or if I don't put any restriction on explored or unexplored set, so that does not make any difference, because ultimately means when I'm reaching close to that goal, so this distance will reduce. So for example, you can see that once you once you are going back to this array, so this distance is increasing. Okay, so it will not be picked for the next exploration. So from Sibiu, I can go back to Arad, and then I can go back to Fagares, I can go back to Aradia, Romanicu, Vilcia. And now out of these possible options, what are all possible actions? Possible options, I have list of frontier. Frontier means the nodes which can be explored. One is Fagares, Oradia, Reminiku, Vilcia, then Temisora, then Serin. So these all are possibilities which I can explore next. Out of all these, so what is the least straight line distance to Bucharest? It is Fagares. So I'll explore this Fagares first. The moment I explore this Fagares, I reach to Sibiu. I can go back to Sibiu once again, and I can reach to Bucharest. So this is my goal. So I have reached to Bucharest, from Arad to Sibiu to Fagares to Bucharest. Now, what it is doing, so if you remember that in case of BFS and DFS, we are not having any idea about the goal. Here, what we are trying to do, we are trying to be pulled. Means this Bucharest is trying to pull us towards itself, because we have a heuristic, or we have information regarding this Bucharest, and that we are trying to minimize at each and every possible node, and that is giving us a pulling force towards the goal. So that's how we move in case of that's how we plan. We develop a navigation problem. We define a navigation problem for robot as well. Okay. Now, this greedy best first search, it gives you Arad, Sibiu, and Fagares and Bucharest. So this is my final path to Bucharest. Okay. Now, the another algorithm is a heuristic based algorithm is that A star algorithm, which is quite popular, and it is this is the algorithm which is being used in case of Google Maps as well. So here the evaluation function is Fn equals to Gn plus Hn. So the path traveled will also be considered apart from the path what is to be traveled from that particular node wherever you are reaching. Okay, so this becomes my total function. So it's a combination of uniform cost search, where we were only considering this GN, and this greedy best first search method, which we discussed just now. Okay, so it's a combination of both of them. Okay, so now we'll see that how does it explore this particular problem from Arad to Bucharest. So if I start in Arad, so what is the cost path cost. Path cost is 0, and then heuristic cost, that is the cost to my goal state is, or the estimated straight line distance is 366. So overall, the evaluation function is 366. At arrest, I have only this option to explore. Okay, now the moment I explore, I expand this arrest, I reach to Sibiu, and from arrest to Sibiu, it was 140. The path cost was 140, and from Sibiu to Bucharest, it is estimated cost is 253. Similarly, if I reach to Timisoara, so Timisoara, from Arat to Timisoara, the path cost is 118. It can be anything. It can be time, it can be kilometers, it can be anything, any parameter of interest to us. Okay. Now here you see that from Timisoara to Bucharest, it is 329. The distance, the estimated straight line distance is 329. Similarly, if I calculate for Zerin, so the path cost is 75, and from this Zerin to Bucharest is 374. So altogether, I get 3 evaluation function for 3 nodes, different nodes. 393, 447, and 449. So 393 is the least out of all these possible options. So what I do, I'll explore this particular Sibiu. Okay. So the moment I explore this Sibiu, I can reach back to arrest because it's a bidirectional problem. I can once again reach back to arrest. There is no issue in that. The only thing is that arrest to Sibiu was 140, and then Sibiu to arrest, once again it will be 140. So cumulative cost we are going to consider. Okay, so 140 plus 140 becomes 280. Okay, and then from Sibiu to Fagaras it is 140, and then it is 99. So Sibiu to Fagaras is 99, and this 99 is being added in this 140, and it becomes 239. So cumulative cost we are getting to reach to Fagaras, to reach to Oradea, it is 291, 140 plus something of this, and then it is becoming 291. For Remini-Vilsia, it is 220, and then this is nothing but my heuristic. From Fagaras to Bucharest, it is 176, as we have seen earlier. From Oradea to Bucharest, it is 380, and then from Remini-Vilsia to Bucharest, it is 193. And then these are all other possible nodes which are there in the frontier. So they are not lying idle, they are also being considered at each and every step. So all the white nodes you can see. So these gray nodes are the nodes which have been explored. All the white nodes are in the frontier list. Now, if I consider all the frontiers, so it is 449, 447, 413, 671, 415, and then 646. So 413 is the least cost or the least evaluation function. So what I'll do, I'll explore this Remini-Vilsia. So earlier I was exploring this Fagaras. Now I'm exploring this Remini-Vilsia. Okay. The moment I explore this Remini-Vilsia, so what I can do, I can go to Sibiu once again. From Sibiu, I'm coming to Remini-Vilsia, and then I can go back to Sibiu once again. And then from Remini-Vilsia, I can go to Craiova and Pititsi. So if you remember this diagram, so from Remini-Vilsia, I can go to Pititsi and I can go back to Sibiu, or I can go back to Craiova. So these all possible combinations are there. Okay, with the path cost mentioned over here. So 97, 146, and then 80. Okay. So all these path costs and paths I am using. So once again, and this path cost to Craiova becomes 366 plus 160 is the heuristic path, heuristic cost from Craiova to Bucharest. And then similarly, if I expand this, So now this is the final evaluation for these 3 newly added nodes in the frontier. Now this has been explored, this has been explored, this has been explored, this has been explored. So what do I have in the frontier list? I have this, all the white nodes are there in the frontier. Now I'll once again compare, or I'll set the priority that which is having this least evaluation function. It is 449, 447, 553, 417, 526, 617, 450, and this and this. So now this Fagaras. Okay, so did I skip something? So I think I skipped something. So this Remini-Vilsia was open. So at this stage, okay, so fine. So at this stage, when we look, so this D, so I think we skipped this D step. So at this step, when we explore this revenue, we'll see. So 526, 417, 553. So this particular figure is having the least cost out of all these open nodes or the nodes in the frontier. So 415 will be explored next. So the moment I explore 450 or this 415 Figueres, I reach to Sibiu. I can go back to Sibiu. I can reach to Bucharest. So this Bucharest can be reached. So this is the goal I have reached, and with the cost of 450. Now what I do, I try to see whether any other nodes are there in the in the frontier. In the frontier means in the nodes available to explore, which is having the cost less than 450. So if there is a node which is having a cost less than 450, there is a possibility to reach to Bucharest from that particular node in less than 450. Okay. So if I explore all these, so this is 447, this is 449, this is 671, this is 646. So this one node I have found, this one node I have found, which is having a cost less than 450. This one node is having a cost higher than 450. This node and this node. So out of all these nodes, this is the only node which is having a cost less, means less in all the nodes. Means obviously less than 450, but out of all these nodes, this is the least cost or least evaluation function node. So what I'll do, I'll explore this Pitetsy next. The moment I explore this Pitetsy, so I get to Bucharest in 418. Okay, so earlier I reached to Bucharest in 450, but now from here I have reached to Bucharest in 418. Now I will explore once again that all the frontiers, if they have, if there is any open node which is having the cost less than 418. Okay, in the frontier. So this is 447. So all the white nodes are in the frontier. Okay, so this is 646, 671, 447, 449, 591, 450, this. So 418 is a least cost node. So it means that reaching to Bucharest is cannot be less than 418. So because all the nodes open available to open are having the cost evaluation function greater than 418. Okay, so it means the optimal path is the Arad, Sibiu, Reminicu, Vilsia, Petetsy, and Bucharest. Okay, so earlier we found something else. So from Sibiu to Figueres to Bucharest. So that was the path given by the greedy best first search method. So okay, so that was not an optimal path. So the optimal path is this one. If you can see this Bucharest. Okay, so if you want to reach to Bucharest in less time or in less let's say minutes or less kilometers, depending upon whatever we have defined as the evaluation function. So this is Arad to Sibiu to Reminicu, Vilsia, Petetsy, and Bucharest. So this is my optimal path, and this is how Google Maps work. Okay, so they consider the straight line distance from between 2 points as the heuristic, and then whatever distance they are moving from, let's say Roorkee to Muzaffarnagar to Haridwar and then to Saharanpur, it will calculate this evaluation function, and that's how it gives you an optimal path. Okay, it is very different from those BFS and DFS methods. So this gives you an optimal means path. Now, after exploring all these things, so this is the last part of today's lecture. So we'll see that how this problem, what we have solved just now with the help of this A-star algorithm, can be framed in terms of robot navigation problem. Okay, so maybe 1 to more slides, and then we'll end this session. If you have any doubts and queries, then we can take up those. For example, this is my navigation environment. And what I'm assuming that my obstacle, so this blue shaded region is nothing but my obstacle. So if this is my obstacle and this is my robot, which needs to reach to this particular inventory section, and it needs to perform some operations over there, it needs to reach to this particular location after overcoming this obstacle. Otherwise, the straight path is this one. So it needs to now how many paths are possible? It can go in this direction close to this boundary wall, and then it can reach over here. It can row, it can reach from this direction to this possible way. It can go from this and then this, then this, then this, like this. So there are multiple ways possible, and each path is having its own time if the speed is constant. Okay. Now I have to find out an optimal path by which this robot can reach to this particular location. This is my start position. This is my goal. So I have defined that this is the goal and this is my start position. And I have also defined that this is my obstacle. Okay, so the obstacle can be defined in terms of means you can install a camera and it can take means you can it can take the live images or live data collection can be done, and then it can define the obstacles. And at this location, it will try to calculate all the paths. So it is having some information about this goal and this environment also, navigation environment, because that much information is required in the problem definition itself. So what I do is in terms of problem for, so this is my raw problem, just a raw problem. Now, how do I formulate the problem in formally? Formally means so that the computer can understand. So if I divide this room, let's say in grids, so this 0, 1, 2, 3, 4. So these are all grids. Okay. So if I divide this room into grids, and then if I try to means if I define that this robot can move in up, down, left, and right. Sorry, right and left directions only. And then this is my obstacle. So obstacle is in the region 1, 2, and 2, 2. So these are the grid locations where the obstacle is there. And this can be updated means by installing a camera, and then it can find out, the robot can find out that okay, so these grids are not allowed to move to cross into. Okay, so the robot can find out. Now, so this is how I'm trying to formulate the problem. So I have divided the whole space into grids. And then in those grids, I have I'm just trying to locate that these are the possible locations where I am not allowed to go. And then this is what my goal state is. So all this information is there. So this is how I have formulated the problem. Now this applicable actions are also defined so that means there is no confusion. So it cannot move diagonally. In actual condition, it can move diagonally, but for calculation purpose, means this problem I have solved, but the time is not there. So that means you can solve it. I give you a framework that how it can be solved. Okay, so the robot can only for simplification purpose, the robot can only move in up, down, right, and left directions. Okay. And these are the obstacles. Now this obstacle for the time being, it is here. For another condition, it can be moved somewhere else. And since this is having a data acquisition system, so this can locate that, okay, so now the obstacle is here. So, or some more obstacles are there. So now these more grids are also not available for navigation. Okay, so this robot can means get in the form of data acquisition with the help of cameras or sensors or whatever means possible. Okay, so we are just trying to see that how this problem can be formulated as can be seen in terms of A star algorithm. Okay, that we have just seen right now. Now you see, now this problem has been defined. It has been formulated like this. So what I have done, I have formulated the problem in this particular manner. Okay, so you can see that these two grids are not allowed to move. Now, what did it do? When this S, this is my robot S, when it moves in this direction, so the step cost is what? The step cost is 1. Let's say for one grid movement, the step cost is 1, or the path cost is 1. And what would be the heuristic cost? So heuristic cost will be from this to this. That is nothing but means if I have, let's say, this is my start position, that is nothing but 2, 0. So 2, 0 is my start position. And the goal node is 2, 4. So 2, 2, and 4. So this is my goal node. The path cost, I'm assuming that it is 1 when it is moving in a particular grid. So for example, if it is moving from here to here, it is 1 path cost. When it is moving from here to this location, to this location, to this location, the path cost is 1, 2, and 3. So the cumulative path cost I'm going to consider. Okay. Now you can see by yourself that the optimal path is it moves in this direction, in this direction, in this direction, and in this direction. Or it moves in this direction, this direction, this direction, this direction, and this direction. The moment it moves, this robot can reach to this goal node through various paths. Like it can move from this to this to this, but it is not an optimal path. Okay. So if you try to look for the solution of this problem with the help of BFS and DFS kind of algorithm, so they will explore all these possibilities and then they will reach to this particular location, goal state. But whereas if you start this by A star algorithm, then in that case you will directly go, you will find the path which is constructed with the help of 2 0, then it will move to 2 1, 3 1, 3 2, 3 3, 3 4, and then 2 4. Or from 3 3 it can go to 2 3, and then it can go to 2 4. So these paths you will be able to find with the help of ASR algorithm, and which are both optimal. So if you try to solve this problem with the help of whatever information we have discussed till now, so you will find this path, which is optimal. Now, this is just a problem means with stationary obstacles, and these obstacles can be anywhere. Means in this grid, or it can means here I have represented with the help of 5x5 grid. It can be a bigger grid. So now you can think of it as a maze puzzle. Okay, so which is very complex, and each grid can be described, and then the motion left, right, up, down. It is very much similar to that. Okay. So now the algorithm can be, this A-star algorithm can be applied, and then you can find out the way towards this goal, okay, which is nothing but there you have to perform some action, let's say with the help of manipulator, or you have to maintain some inventory and all those things. So that is a different task altogether, where we need to understand the kinematics and all those motions, assembly and all those things. So we are not discussing that. So the main idea is the robot navigation. So this robot navigation problem, as we have discussed, it can be solved with the help of A-star algorithm, what we have discussed just now in detail. Okay. So I leave this problem to be solved by you. I have already told you the solution, that it will move in this direction, that 2 1, then 3 1, 3 2, 3 3, 2 3, and then 2 4, or like this, and this. So these two are optimal paths available to this robot. Okay. Apart from that, it can go from this direction, from this direction. These are not optimal paths. So just try to, means you can take a photograph of this particular slide, and then you can try to solve these, this example on your own with the help of the discussion what we have had on A-star algorithm. Since I was told that this is a tutorial or lab-based type of class, so I thought of solving this problem here itself, but because of means time limitations, I'm not able to, means we don't have time to solve this. Okay, so it's better if you can solve this problem. Now the idea here is that this problem can be elaborated. Elaborated means this robot, so this is a very small space of 5x5 grid. It can be a very big space, and then we can define the problem in this manner, and then diagonals are also allowed, and then it can be further optimized with the help of more means realistic things which can be included in this problem formulation. Okay. Now this is means a heuristic function. So when you are not allowed to move diagonally, then you take the heuristic function in the we call it as city box grid, or Manhattan type of distance, where you are moving along these grids. Okay, so this, if you see this red line, and then blue line, and this yellow line, so all of them are having equal distances. The only line which is having the least distance is this green one, which is diagonal. But since you are not allowed to move through these diagonals, let's say you are having some crosses or obstacles over here. For example, buildings are there. So this is named on the city Manhattan, because the city is structured in the form of grids. So there you cannot move in between these grids, or means you can move only on these streets. Okay, so this is why it is called as Manhattan distance. Okay. So this is all from my side. I would share one video. Let us see a video where you can see the direct application of what we have discussed today. Okay. So I'll just stop this sharing and then I'll share my actual screen. Just a minute. Stop it.
Participant may write in the chat box for any query.
So I'll share this one very good example video which I just came across. Let me share my screen.
So we have a query that how can robot deals with sensor noise and uncertainty and incomplete information during navigation?
Just a minute. I'll just show the video and then we'll discuss the problems. Huh?
Yeah, sure.
Just a minute. So are you able to see my screen?
Yeah.
Okay. So you just see this thing of these are nothing but obstacles, as you can see over here. So you can see that this robot is equipped with sensors and it is trying to locate the obstacles and trying to find. So it is moving only on grids. You can see that it is moving only on those lines. It is not moving in between those lines. Okay, and this is possibly the location where the goal is. You can see this green mark papers. Okay, so this is where the location or the goal is. It has to reach to this goal state and which it has reached successfully. So, and if you see this video, so what I'll do, I'll just drop this video in the chat box. You can see and then try to correlate with this.
Yes, sir.
Just a minute. So I'll stop sharing this video and then what I'll do, I'll just drop this video link in the chat box so that you can see by yourself that this is moving with on those grids only. Okay,
Yes.
not on not anywhere. Okay, so it is typically utilizing an A star algorithm, and based on that, it is trying to means it has moved on an optimal path. Okay. So you can see this, and then you can try to solve the problem what we have means I have just shown towards the end. Yes. So the question is that how can robots deal with sensor noise, uncertainty, and incomplete information during navigation? So this is related to the type of sensors or the quality of sensors. So noise and uncertainty. So uncertainty means one very good uncertain phenomena is that if the obstacles are moving, so that adds a lot of uncertainty in the problem, and that increases the complexity as well. So if we need to consider those uncertain things, then the complexity means the problem is not that simple. What we have discussed. So we need to consider means we need to evaluate at each and every moment what is the physical space to move in. So to factor, so regarding sensor noise, means it definitely depends upon the kind of sensor you are using. So if you are means you can use some tools to filter out the noise means which is being generated. So that is nothing but signal smoothing and all those tools you can use. Or you can use a different kind of sensors which are costly and which are not generating a lot of noise. Okay. And then uncertainty, as I told you about those moving obstacles. So then the complexity is it's not a very simple problem in that case. You need to it becomes a very multi-dimensional kind of problem where we need to figure out at each and every instant what is the possible space for navigation. Okay, and then incomplete information during navigation. So incomplete information means the sensor is you're talking about, I think, sensors. Okay.
Right.
So that information is required. So incomplete information may lead to collision and all those instances. So it depends upon the quality of sensor and how well you have defined the problem. So that is also an important part. Okay. So like we saw in the video, so there may be some proximity sensors as and when it is reaching close to that object, it is basically finding out that object is there. So it does all the calculation before starting. So it runs a A-star algorithm before starting from the source to the destination. It finds out the optimal path and then it starts navigating that optimal path. So this is how it works. So complete environment information is required before you start navigating the space.
And
So
so
I
there is
hope.
another question.
Sorry. Yes.
So there is another question. How do robots coordinate their paths in multi-road navigation without collision or any deadlock?
Yeah, so as I told you that multi-robot navigation is not it's once again that problem of when obstacles are moving. Okay, so they need to define the space at every moment. That so the environment information is very critical. As I told you, when you are defining a problem, that is very important. So when you are defining a problem, then you need to define that other robots are also operating and they need to connect. Okay, for example, when we are driving cars, okay, so self-driving cars. So that is nothing but a multi-robot kind of environment. Okay, so where each and every driver is acting like a robot. So they need to communicate properly, even if they are not communicating directly. So they know that at what speed the front car is coming or the car is overtaking. So all that information needs to be collected with the help of different sensors, and it is no longer a simple problem what we have discussed. It becomes a multi-dimensional problem once again. Okay. So, if we try to find out, means if we try to develop a robot soccer game, so there also we have multiple robots or agent or players acting, and then we need to act accordingly. So those kind of problems are not that easy to deal with, or they have the way a multi-dimensional problem, the way we discussed that assembly problem. So it is also not a very simple problem, though it might means I don't know whether you could appreciate that or not, but it was a very difficult problem to explore. Okay.
Okay, sir. Is there any query? Participant may write in the chat box. So on behalf of organizing committee, I would like to especially thank sir for accepting our invitation and delivering the very insightful lecture on this note. So thank you, sir, once again. Thanks a lot very much.
Thank you. Thank you very much.
Thank you, sir.
So I'll just log out of this
Yes, sir. Yes, sir.
window. Okay. Thank you.
Thank you, sir.
Okay.
Participant B will have the next session at 4:30 after a short tea break. Thank you.